Okay, so the last thing that we have seen was this modulation property. We were calling this the modulation property due to a communication system terminology, as you may guess, because it requires multiplication in time versus convolution in frequency. Whatever you do in time domain, you have a counterpart in the frequency domain. For example, if you convolve in the time domain, it means you are multiplying in the frequency domain. And conversely, if you're multiplying in time domain, then you convolve in the frequency domain. This modulation property was one example of multiplication in time versus convolution in frequency. What was the signal that we were multiplying in time domain? It was multiplication with a cosine, which has, so if we start from here, so if the top figure corresponds to the Fourier transform of your band-limited signal, it could be any shape, but it's easy to draw a triangle. That's why we always draw that. When you multiply your x of t signal with a cosine omega ct, where omega c is the carrier frequency, that c notates the carrier over there for omega c. When you multiply in time, whatever happens in the frequency counterpart is the convolution of the Fourier transform of x of t, which is x of g omega, with the Fourier transform of cosine. And we know that cosine Fourier transform corresponds to two impulses at omega c and minus omega c. So when you convolve your triangle shape with these two impulses, what you do is you carry those two triangles to the position of the impulses to get this final shape, two triangular shapes, two band-limited bandpass shapes. Those omega c's are quite high frequency in normal telecommunication applications. Therefore, they can be transmitted through the air to the other side. And what the other side does is precisely the same. It gets the signal, those two triangles. By the way, some other stations are also transmitting at other frequencies. Not omega c, but omega c prime. Those triangular shapes corresponding to different stations, they mustn't overlap. Otherwise, it means the channels are interfering with each other. So, when you tune to one of these signals, what your radio does is it applies a bandpass filter to take only these triangles, and then it multiplies your reception z of t with cosine omega ct again. When you do that, graphically what happens is the following. Your received bandpass signal is at the top, and in frequency domain you convolve with again these two impulses. And when you do that, it means you're shifting those two impulses to the right and to the left to make two replicas of those two triangles, at the right and at the left. And then when you combine them, you will see that you get the same triangle in the center. The two triangles come on top of each other to form exactly the original triangular shape. And you have some extra coefficients. Those two coefficients are at minus 2 omega c and 2 omega c, which are very far away from the baseband. So you can just low pass filter the origin, and that corresponds to demodulation, radio reception. This strategy is also known as the amplitude modulation technique or a linear modulation technique. And it's the fundamentals of telecommunications, we can say. But of course, this is not the only example that we can think of for applying the modulation property. For example, suppose that you have a modulator. A modulator means multiplication with a cosine or multiplication with a sinusoid in general. It could even be a complex sinusoid. By the way, one of your friends have asked me during the break about how to even multiply two signals. How can we multiply your x of t with a cosine? You have seen electronics, you have seen circuits, right? Can you think of a circuit to multiply a baseband x of t with a high frequency cosine? How can you even multiply two signals? What's the circuitry which multiplies signals? That's a problem. And it's a technique. But of course, in electronics, we have circuitry to do that. And there are several methods, but those methods are dedicated to the next semester's Introduction to Communication Systems course. So you will see a lot of techniques over there. Now, suppose that you can multiply with a complex exponential or a sinusoid, and you have only a low-pass filter. You are a poor man. Although you can multiply with something, you cannot just apply a band-pass filter. How can you perform a band-pass filter using a low-pass filter? That is the question. And I'm going to just briefly give you hints about how to do this, how you can do that. In fact, it's not the poor man's job that I will describe. It's the rich man's job to do it that way, because in signal processing, there are very nice low-pass filters. They have been implemented circuit-wise. And what I mean by nice low-pass filters is that they are quite close to exact low-pass filtering, very sharp. Their quality factors are very high. So the transitions, etc., they are very nice low-pass filters. Usually the filters are designed in the low-pass domain. And high-pass filters or band-pass filters are not very good. They have lousy transitions. So if you want to have a very good band-pass filter, what you do is you shift your band-pass signal towards the origin first in the frequency domain. Suppose this is the high frequency or band-pass range. You just pull it to the low-pass region, around the DC, and then apply a low-pass filter, which is very nice, as I repeat, and then push it back to its origin, to its original place. That would mean, effectively, a very nice band-pass filtering, isn't it? So that's what you can also do. So if you have a signal, you can first modulate it with a complex sinusoid by multiplication with e to the j omega 0 t, and you have y of t. That y of t could be something like this. Suppose your signal's Fourier transform is a band-pass signal like this, where this is omega 0. When you so this is x of j omega. When you multiply your time domain signal by e to the j omega 0 t, what you mean is that you're essentially, it must be minus omega 0, so e to the minus j omega 0. You're pulling this shape at the right hand side around the origin. So we can say that y of j omega is sort of like this. Okay. Then you apply a sharp low pass filter, for instance, as sharp as this one, and then the result will be, let's call it z of j omega, excuse me, and the situation, the shape will somehow look like this, whatever. And finally, these are all on the axis of omega. Finally, what you do is, this time you multiply z of t by e to the j omega 0 t to have, let's call, f of t. And f of t will be, again, such a function that its Fourier transform will look like this. So effectively, f of j omega is a bandpass filtered version of that x of j omega at the top, but with a very sharp bandpass filter. You just cut around omega 0 very sharply. And the best method to do it is like this, because your sharpest knife is around the origin. It's the low pass filter knife. It is sharp. The others, band pass, high pass, etc., those filters are not so sharp. Right? So this is a technique that we can use as well for the modulation technique. Now, my final remarks about this continuous time Fourier transform is regarding the solution of differential equations and providing the fundamental link between the impulse response or the inverse Fourier transform and the frequency response, which is the Fourier transform itself. And that is the linear differential equation portion, let's call it linear differential equations. And it's a good idea to start with an example. The example is a first order differential equation like this. This is a first order linear differential equation, and the order comes from how many times you differentiate the output. The order is not related to how many times you differentiate the input, by the way. It is related with the output. This differential equation normally has two solutions, right? Two parts of the solution from differential equations. Do you remember those things? One of them was the particular solution. The other one was the homogeneous solution. So, in this methodology of Fourier transforms, we are not interested in the initial conditions. So it's not the part regarding the initial conditions. So it's not the particular solution. It's the homogeneous part that we're looking for. And we know that, I know that you had been using the Laplace transform already, the S variable, to solve it. Now, there is a strong relation with S and the Fourier transform. And as a matter of fact, here, what you have is S is equal to j omega. Because we know that when you take the Fourier transform of this equation, both sides of this equation, you will have this kind of a situation. What is the Fourier transform of a derivative of a signal? J omega times, exactly. So there it is. Oops, it's not x, it's y of j omega. And the Fourier transform of this part is plus a times y of j omega is equal to this part of the equation, x of j omega, isn't it? So it truly looks like the s times ys plus ays is equal to xs. That's what you have been doing in differential equations. And s is equal to j omega. It comes from the property that we have seen last week. And since everything is in the x and y in the Fourier domain, we know that the filtering is nothing but y of j omega divided by x of j omega. What I mean is this, or let's put into a parenthesis, y of j omega parentheses at the left hand side. J omega plus a in y of j omega parentheses is equal to x of j omega. Now what I say is the following, or we can write it like this, y of j omega is equal to 1 over j omega plus a in a big parenthesis times x of j omega. Now this portion is nothing but h of j omega. Because x of j omega times h of j omega is y j omega. Why is that? From the convolution versus multiplication property. We know that y of t is equal to h of t convolution x of t, isn't it? So in frequency domain, what is it? It is y of j omega is equal to h of j omega multiplied by x of j omega. So this thing, what we have here inside the huge parentheses is h of j omega. Or you can say it like this. H of j omega is always y of j omega divided by x of j omega. It's a very convenient formula to use to find the input-output relation. And you cannot do it in time domain. You cannot say that ht, the impulse response, is equal to yt over xt. It's not true. Please do not write it that way, because I am sure in some of the examinations I will encounter this. Some of the students who are not here today, probably, will write in their examinations, ht is equal to yt over xt. They will write it, which is very incorrect. But in frequency domain it is correct. In time domain, y of t is ht convolution xt. That's a very different operator. It's not multiplication, it's convolution. But when you take the Fourier transform of every side, this is what you can have. And this formulation in frequency domain will help us to solve any kind of differential equation input-output relation, either in the form of frequency response, because what's the frequency response? The frequency response is 1 over j omega plus a. And what is the impulse response? The impulse response is the inverse Fourier transform of h of j omega. That's the inverse Fourier transform operator that I'm indicating. So you need to find the inverse Fourier transform of 1 over a plus j omega. And do you know what the Fourier transform of 1 over j omega plus a or a plus j omega? Do you remember that? It is the first example. E to the minus at u of t. So this is the impulse response, and you are clear. Excellent. A very easy way to find the impulse response. Now, therefore, we have a three-port triangular shape, which I can ask. I can give you any part of this triangle, and I can ask you the other two, or any of the other two. One of them is clearly the impulse response. It's one of the first things that we have seen. Or I can give you the frequency response or the Fourier transform. So the relation between h of t and h of j omega is the Fourier relation, forward Fourier transform or inverse Fourier transform. And now we have the differential equation. Formality. If I give you the differential equation, input-output relation, the way to solve a question is to start from the differential equation and come up with h of j omega first, and then take the inverse Fourier transform to come up with h of t. So that is the path to follow. Just the opposite could also be given to you. I can give you the impulse response. The impulse responses will usually be in the sense of exponentials like this. 2 or 3 exponentials may also appear. And can you guess what 2 exponentials will correspond to? It will correspond to 2 terms. One of them is, one of them is 1 over j omega plus a. The other one will correspond to 1 over j omega plus b, for example. And when you combine those 2 rationals of j omegas, they will correspond to probably a second order differential equation, unlike the first order differential equation here. Or, let's now reverse the question. I can give you a second order differential equation. From there you take the Fourier transform of the equation, both sides of the equation like this. and then you will come up with y of j omega divided by x of j omega with two such expressions, probably. And those two things will correspond to two exponential terms in a impulse response. Yeah.
Bunlar artı şeklinde mi? Artı, yani bir toplanacak mı hocam? 1 bölü j omega artı a ile 1 bölü j omega artı b toplanacak.
You have to expand it in the expression. You have to simplify it. It may be in the term of in the case of in the sense of summation, or it may be in the sense of multiplication. You just need to expand it in either way. We will see examples of both types. One of the types will require summation. The other one will be in the form of multiplication. We will see examples regarding that. In fact, why don't we just find another example here. Oops. Example is the following. The second derivative of y of t plus 4 times d by dt y of t plus 3y of t is equal to d by dt x of t plus 2x of t. This is the input-output relation given in the form of a differential equation. By the way, if you just go and watch the first hour lecture, you will see that it starts with differential equation examples for circuits, RLC circuits, and damper and spring mechanical equations. They always come up with the same second order structure. So if you can solve a second order differential equation input-output relation, then it means that you can find the impulse response of a circuit, of an RLC circuit, and you can find the impulse response of a damper and spring coil mechanical system as well. As a matter of fact, there is a whole chapter dedicated to second order systems because they are physical systems normally. But for us, it's not very critical. You just need to know the idea about how to handle such dynamic systems. The Fourier transform is the thing that I will try. The second derivative's Fourier transform is what? It's j omega times j omega again. So that would correspond to j omega in parentheses square y of j omega plus 4j omega y of j omega plus 3y of j omega is equal to j omega times x of j omega plus 2x of j omega. And all you need to do is you need to find y of j omega divided by x of j omega, but both the left hand side and the right hand side of the differential equations can be put into parentheses of y of j omega and x of j omega. It's quite simple. And you will see that h of j omega, which is again y of j omega divided by x of j omega, is equal to j omega plus 2 divided by j omega square plus 4j omega plus 3 in the denominator. So this is h of j omega. Now, in order to solve these things in terms of two additive exponential components, by the way, you have to do it that way. I don't recommend that you find it in the form of multiplication of two first order systems, but try to do it in the form of two first order systems. This is a second order system. There is an omega square in the denominator. So how can we make it the summation of two first order systems? What are the denominators of those two first order systems? We will have to start from there. J omega square plus 4j omega plus 3. You have to just separate it into multiplications of two first order polynomials of j omega. The first one is j omega plus 3 and j omega plus 1, I would say. You can find the roots if you wish. But if you just multiply them, it will be j omega in parentheses square. 3 will come and 1 will come from there, which will make 4 j omega. Plus 3 times 1 is 3. So it's a simple expansion. Usually in the questions you will come up with such easy to expand things. Otherwise it will require some square roots, and you know how to find the roots of a quadratic polynomial. Minus b plus and minus. Yeah. So now the numerators is an issue. How do you find the numerators? There are several methods that are described in calculus books and in the Oppenheim's book as well. For example, you put the root of one of the denominators, substitute it into the system and find the scale and things like that. And I'm not very keen on these things. I mean, I don't really know precisely how to attack these problems. I usually do it like this. I put an A here and the B here, for example, and try to find A and B by multiplying with the cross multiplications and solve for A and B to make A times this plus B times this to be equal to j omega plus 2. That's a good idea, I guess. And by the way, since the numerator is in the order of j omega only, this will be A and this will be B without any j omegas or anything. However, if the numerator is, for example, j omega square or something like that, you will have to put not only B, for example, here, but plus C times j omega over there to find the extra coefficient. There will be 3 equations to find 3 unknowns. But the number of unknowns in the numerator is the coefficient of j omega and the coefficient of the real number. So you have 2 unknowns. That's why you have A and B here. So when you solve for A and B, I'm not going to do that, as if you already know me, you know that I'm not going to do that. They are both 1/2. They happen to be when you solve it. So this whole expression of the second order system is nothing but the addition of 2 first order systems. And we know the inverse Fourier transform of both sides. So this is h of j omega, and the inverse Fourier transform of h of j omega is h of t, is equal to the inverse Fourier transform of the first one is 1 over 2, of course, because of the numerator expression, e to the minus 3t u of t, okay, plus 1 over 2 e to the minus t u of t. That's it. This must be the impulse response. The questions may become a little bit more complicated, other questions that you may encounter. For example, what would you do if you have in the numerator something like this? Not only 1 over 2, but something like this. 3 plus 2j omega divided by j omega plus 3. This could also happen to you. Then how would you attack this problem? Then the way to attack such a problem is to separate, first of all. Like this. First separate it, split it. Then the first one will be 3 times e to the minus 3t u of t. How about the second one? It's going to be like this. 2 times e to the minus 3t u of t. And because of this j omega, you need to take the derivative. The time derivative of this thing. Can you take the time derivative of that thing? So as you see, you're in the 3rd class, but you still need calculus, basic elementary calculus, to take the derivative of these two, because The derivative of the multiplication of two functions it has two parts. One of them is the derivative of the first part multiplied by the second, and the other one is the derivative of the second part multiplied by the first. Okay? You have to be very careful. And the derivative of u of t is what? Impulse. Delta t. Delta t will come into the picture somehow. Alright? So, this is the way to attack the problem. And the solution of this, I'm leaving to you, of course, as usual. But the strategy to solve such questions is this. So you have the differential equation at the top, and then you take the Fourier transform of both sides of the differential equation, and you develop a formula for h of j omega to be equal to y of j omega divided by x of j omega, and try to simplify it to first order systems. That's what you need to do in order to find the inverse Fourier transform. If I ask you the inverse Fourier transform, I mean if I ask you the impulse response in time domain, of course. If this relation from here to first orders is too difficult, then probably I wouldn't ask you to find the impulse response. Then I will only ask you find the frequency response. And you will say this is the frequency response, and you will get full credit from there. Okay, is that clear? This is the way to relate time domain, frequency domain, and differential equation, input-output relations of the system. 3 ways to represent a system. 3 fundamental ways to represent a system. So, for instance, let's go back here. The question could be asked like this. There is a system with impulse response to be equal to this. Or in 1 over 2 u of t parentheses, e to the minus 3t plus e to the minus t. And I ask you the differential equation, the input-output differential equation which governs this system. Then how will you do it? You first find the Fourier transform of this h of t and say h of j omega. And then try to compact this thing to get this equation. And then you will say that it's y of j omega divided by h of j omega. Then do the cross multiplications to come up with the top equation. And from there, since everything is in the form of j omega or omega squared, you can easily translate this thing by inverse Fourier transforming into a differential equation. So the question could also be in the reverse direction as well. So is that clear now? Because this is the last issue that I would like to talk about in terms of the continuous time Fourier transform. And I'm going to give a break of the continuous time Fourier transform now. I will stop this video and I will give a 15-minute break early, because after the break we will start with the discrete time Fourier transform version, which I'm not really very happy with it. It's a tad more complicated and more counterintuitive as compared to the continuous time. The continuous time is usually easy. They are related with physical entities like circuits, RLC circuits and things like that. In discrete time, it's a little bit more complicated, so we will need some time to cover the discrete version of this Fourier transform. Okay? So let me stop this video right now.